So today we'll study about differential equations, direction fields, and how to use differential equations to solve certain problems. So to motivate ourselves about differential equation, consider the following problem. So a skydiver is in a free fall after jumping out of the plane. So basically there's a skydiver here. And he's in free fall. Now think about the forces acting on the skydiver. So there are two forces acting. One force is acting downward, which is due to the gravity, which is Fg is mass times the gravitational acceleration, which is 9.8 meter per second square. And there is a force acting in the other direction, which is the drag or the friction. And that force is the force due to friction, and that is directly proportional to the velocity. In fact, it is given by minus gamma g, where gamma is a drag constant. Okay, so gamma is a constant. So these are the two forces acting, and consequence of these two forces, we will get what? We will get the motion in the downward direction. So this will be your force with which the net force with which the skydiver will be coming down. So we get, sorry, it's gamma times V. Thank you, that's correct. So therefore, what do we get? We get F net, which is mass into acceleration, which is same as m times dv by dt, is equal to, now this force is acting in the, net force is acting in the downward direction. So since we are taking that, we'll take this with positive sign, and gamma is acting in the opposite direction of that. So we get gamma v. So we get F equals to, so we get dv by dt. So therefore we get dv by dt, or m times dv by dt, equals to g minus gamma by m v. So where m is, F is net force, m is mass, right? M is mass, v is the velocity of the object, and a is the acceleration. The point is that this equation here captures the motion of the object under the gravity along with the air friction. So as we see that it has a derivative inside it, such an equation is called differential equation. Yeah, because there is a derivative involved in the equation. So this equation captures the motion or the free fall of the skydiver under two forces. Note that there could be more than two forces, but for simplicity's sake, we are taking two forces in consideration here. So this is an example of a differential equation. Now let's look at a few more differential equations. So one is the anti-differentiation, can be also thought of as a differentiation and differential equation, because we have what? Y prime equals to x plus sine x, right? So the way we solve for it is we say, well, y is integral of x plus sine x dx, right? So this is an example of a type of differential equation. One is the natural growth. So we have seen this, the derivative of the function is proportional to the function itself, right? So here the derivative of the function is proportional to function itself. And in this case, we have seen the solution is P of x equals to K times or C times e to the power kx. Here you can check why is that the case, because this implies dp by dx is C e to the power kx multiplied by k, which is your kp. So you have seen this example in the population growth. Another example is from Newton's law of cooling. So if we let y equals to T minus m, this equation becomes, this gives us dy by dt equals to ky, and then the solution becomes, this reduces to a natural growth problem, right? Reduces to solving natural growth problem. In this case, recall, you had, this was your time, this is the ambient temperature, and this was your temperature, right? So you have an object of temperature T, you place it in the surrounding of ambient temperature M, and you basically see how is the temperature of the object changing. Another one is the logistic growth. We will see the solution of it in soon. So logistic growth looks like there is a maximum carrying population, and then this is how the logistic growth curve looks like. We will solve this. Okay. Now, so now the question to ask here would be, well, we can't solve it, but do we know when is dp by dt equals to 0? So such a point is called equilibrium point. When the system is in equilibrium, that means there's no change. That means the derivative is 0. And that would happen when p equals to 0 or p equals to m. Similarly, in this case, an object falling under the gravity, if you ignore the friction, you have mg equals to m dv by dt. So, but your v is ds by dt. So therefore we get dv by dt square. Sorry, dv by dt is d square s by dt square. And that will be, if you divide both sides by m, you get g. Similarly, then the Hooke's law is a motion of spring. So the idea is you have a spring to which you have attached a mass m. Then if you have a motion here from the x, and we get, in this case, we have F equals to ma. So therefore we have A equals to F over m with the minus sign. Sorry, F over m, and this is going to be minus kx over m. This is Hooke's law, basically. So Hooke's law says that the force exerted on the spring is proportional to what? Is proportional to 1 over mass and the elongation distance, right? So the force is proportional to the elongation x of the spring. So we are essentially solving then in that case, what is the acceleration? D square x by dt square, that is going to be minus k by m times x, where x is position from the equilibrium position. Okay, so there is an equilibrium position in which the spring is stable, and then when you from the equilibrium position, and a is the acceleration. So the idea is the following. Actually, the bigger picture is that differential equation captures so many different scenarios. So again, what is a differential equation? A differential equation is an equation that contains an unknown function and one or more of its derivatives. The order of differential equation is basically the order of highest derivative that occurs in the equation. A function f is called solution of differential equation if we have y equals to f of x and its derivative are substituted in the equation, then the equation is satisfied. What does it mean by solve a differential equation? To solve a differential equation means to find all possible functions that satisfy a differential equation. So let's see a few examples from the past. So here, x double prime equals to minus k by m x. So here unknown function is what? X equals to xt is an unknown function. What is the order of differential equation? Order here is, what is the order of highest derivative occurring here? The order of highest derivative occurring here is 2. So order is 2. What is the solution? So we'll see later how to find solution, particularly to the first order differential equation. This is going to be, one solution you can see is going to be sine of square root of k by m t. And solving for f of x can be involving. Solving for f of x can be tricky here. Okay. So this is what is an example of a differential equation. So now, what is the initial value problem? Initial value problem is a differential equation together with some initial condition which must be specified value that function must satisfy. So initial condition is presented in the form of y of t naught equals to y0, which says that we want a function y which satisfies the differential equation and has value y naught at t naught. So let's see an example and things will become clear. So first of all, let's look at the following differential equation. So first of all, what is the order of this differential equation? Order is 1. Now, here we are asked to show that this differential equation has a solution y equals to square root of x plus c. So let's see. So let's sub this into the equation. Substitute y equals to square root of x squared plus c in the above equation. So we get LHS is dy by dx, which is going to be, what is derivative of this guy here is going to be 1 by 2 square root of x squared plus c multiplied by derivative of inside, which is this, which is going to be x upon square root of x squared plus c, which is x over y, which is RHS. So therefore, this implies y equals to square root of x squared plus c is a solution. Next, so show that y equals to e to the power 2t is a solution to the second order differential equation d square y by dt square plus dy by dt minus 6y equals to 0. So first note that this is a second order differential equation. Why? Because the highest derivative is 2. So now we need to check whether this is a solution. So we have, if y equals to e to the power t 2t, we have dy by dt equals to 2e to the power 2t and d square y by dt square equals to 4e to the power 2t. So therefore, LHS, the left hand side is going to be d square y by dt square is going to be 4e to the power 2t plus dy by dt, which is 2e to the power 2t minus 6e to the power 2t. That is 0, which is equal to your right hand side. So as required. So this is indeed a solution. Now similarly for B, we should check. So same story here. What is d square y by dt square? What is dy by dt? So that is first thing to calculate. If we have a y equals to e to the power minus 3t, then dy by dt is minus 3 e to the power minus 3t. And the second derivative of that is going to be 9 e to the power minus t. So therefore, the left hand side of equation is going to be 9 e to the power minus 3t plus e to the power minus 3t minus 6 e to the power minus t. So if you add this, you'll get 9 minus 9. So this is again 0. To RHS as required. So what is the upshot? Therefore, these two are the solutions to this differential equation. Okay. Now let's look at the following problem. So the value of c, so that y equals to square root of x squared plus c is a solution to the initial value problem. Dy by dx equals to x upon y, where y of 0 is 3. So what it means by initial value problem? So you're given initial condition. It means what? This read. How do you read this condition? You read when x is 0, y is equal to 3. So let's solve this differential equation. So we already have seen from part 1 here you have already seen that this is a solution. Yeah. So we already know that this is a solution. So we already know from above that y equals to x squared plus c is a solution. Now we can find the c by having the following, but y of 0 on one hand is 3, on the other hand it is what? 0 square plus c. So this gives me 9 equals to c. And therefore, what is the solution? Y equals to square root of x squared plus 9 is the solution to the given IVP, initial value problem. Now, sometimes if you're given a differential equation, it's easier to visualize the solution rather than finding it. So we now look for visual approach to first order differential equation. Consider dy by dt equals to 3 minus y. So if y equals to f of t is a solution, fill out the values in the following table and use that information to sketch the graph f. So how do we do that? We take minus 3, we, we have y is 1. So find out dy by dt at minus 3 and 1. So dy by dt is going to be what? 3 minus y. So 3 minus y is going to be what? 3 minus y is going to be 2. Similarly, when t is minus 3, you still get what? 1. Then if you have minus 3, you take this to be 3, you get what? 3 minus 3, 0. Similarly, if you take t to be minus 3, you take 4, you get minus 1. You take minus 3, again you take 5, you get minus 2. Let's fill in few more values. So you see that the values on this side are independent of t. So let's draw the direction field. So how do we draw this? So at 3, minus 3, let's look at the first entry. So at minus 3 and 0, so this is your t, this is your y. And at minus 3, 0, so when t is minus 3 and when y is 0, we are here. At this point, draw a line of slope, a small line segment of slope 2. So how do you draw a small line segment? So I'll take one run unit, 2 rise unit. And then I'll draw a small line segment like that. Now note that as long as your y is 0, no matter what, your solution will be, your dy by dt would be the same. So let me just draw it anyway. So they will all have same slope. Now this doesn't happen for all the differential equation, but in this case, since the right hand side is independent of y. So okay. All right, so we keep drawing line segments of slope 2. Okay. Now, so line segments of slope 2. So let me complete the drawing. You don't need this big of a line segment. Uniformly okay, so on and so forth. Now, what about when y is 1, when y is 1, we'll get what? 2. No matter what your t is, you'll get, when y is 1, the slope will be 2. And when y is 0, the slope is 3. So here we need slope 2, these points. So when y is 2, the slope is 1. So it's going to be, these lines have slope 1. And when y is basically 0, when y is 3, you get dy by dt 0. So at y equals to 3, the slope will be 0. Now let's look at the following. When y is minus 1, the slope is going to be 4. And when y is 4, the slope is going to be minus 1. So at 4, the slope is negative. At 5, the slope is minus 2. So if you want to find out, so first of all, this line here, this is called equilibrium. Now, if you want to find a solution, you just trace one of the along one of the direction fields, you will get one solution, right? Another solution is here. So here we have y of 0 is, say, if y of 0 is 2, then you basically take this solution. When y of, so this corresponds to y of 0 equals to 2. This corresponds to y of 0 equals to 5. Another solution would be, say, if you walk along this solution, this will correspond to y of 0 equals to 0. Y of 0 equals to 0. So this is how you get the solution to the differential equation, by drawing this, which is called the direction field, or also called the slope field. So again, what are you drawing? You're drawing t versus y, and at every point t and y, say at t equals to minus 3 and 1, minus 3 is t, and 1, you draw a line segment of slope 2. So any curve, so remark, any curve that we draw to this direction field is what? Is a solution. So you see, this differential equation has many solutions, but the initial condition, let's us pick which one. So if we look at this example here, this is how the curve looks like. So if you look at this, it will basically look like a concentric circles. So the solutions look like concentric circles, x squared plus y squared equals to c squared. Now note that sometimes it's easy to find the solution, but sometimes the direction field is the best way to understand the solution. Okay. Now let's match the differential equation with corresponding solution. So if we notice here, in this case, so here what we get is, here we are getting, at this point, we are getting some kind of an equilibrium really, right? That the solutions are becoming zero. That the equilibrium at y equals to 4, we are getting what? The solutions are becoming zero. That is, y prime is becoming zero. So therefore, here in this case, at y equals to 4, it's becoming zero. So this is same as C. Now note that in this case, y prime is 1 plus y square. So that means what? The derivative is always positive. The function is increasing and y prime never becomes zero. So look at these ones. So among these ones, you see that these guys are always increasing. Yeah. All right. And there's no equilibrium. So therefore we get, if we have to match it, we'll match it with basically A. If you look at this guy here, we have that somewhere around the line y equals to x, we are getting a equilibrium. So A must be, so this must be your B. Yeah. Another way to look at this is the only one which depends on x, right? Here you see it is invariant of y. These curves are exactly the same based on y, or not based on x, right? Whereas here, this is the only one which depends on y. If you're here, it's going down, but if you're here, it's going up. So therefore, the only possibility among these three would be y equals to x minus. So now let's look at another example. So consider the slope field dy by dt equals to minus y times y minus 3. The slope field is given below. Sketch a curve whose initial conditions satisfy y of 2 is y equals to 2 and t is 0. So let's see. Let's go here and see when is y of 0 2. So y of 0 is 2 is somewhere here. So now we have to trace the curve. So the way you trace it is you basically go like that. So this one gives you what? Y of 0 is 2. Let's trace the other one. When y is 0.5, t is 0. So y is 0.5 and t is 0. So y is 0.5, when t is 0, y is 0.5. So somewhere here. So let's trace the curve. It goes like that again. And we have, so this is the other solution. Yeah. So now note that these values at which the change is becoming 0, and also this one here, we say y equals to, so dy by dt equals to 0 when y equals to what? Y equals to 3, 1, or 0. These are called equilibrias, plural for equilibrium. So there is a numerical method of approximating the solutions, but you will see more of it in MACM 316. Yeah, using Euler's method.